Have you ever watched thousands of starlings paint breathtaking patterns across the evening sky? Or marveled at the intricate, bustling highways of an ant colony? These aren't just beautiful natural spectacles. They're examples of swarms, groups achieving incredible collective feats through seemingly simple individual actions. But this isn't poetry. It's a cutting-edge field of science, driven by surprisingly elegant mathematics. We're diving into the calculus of swarms, uncovering the mathematical blueprints behind collective intelligence, and how they're revolutionizing everything from robotics to economics. At its core, swarm intelligence is about how decentralized, self-organized systems create intelligent global behavior. Think about it. There's no single leader in a flock of birds or an ant colony. Instead, individuals follow basic rules, reacting to their immediate surroundings and neighbors. Yet, from these local interactions, complex adaptive group behaviors emerge: efficient foraging for food, smart decision-making, even intricate construction projects. So how do we decode this? Mathematical modeling is key. Scientists use a rich toolkit, including ideas from calculus, statistical mechanics, and graph theory, to translate swarm behaviors into predictive frameworks. For example, differential equations can describe how individuals move and cluster, helping us understand how information spreads and how a swarm makes a collective choice, like finding the best new nest site. We also use models to analyze the probabilistic nature of individual actions and their combined effect on the group. One fascinating area is understanding the trade-offs. How does a swarm balance exploring for new resources versus exploiting known ones? Mathematical models help us analyze this vital explore-exploit dilemma, showing how individuals, by observing others, can collectively find optimal strategies. There is even talk of a dedicated swarm calculus, a set of general principles to predict and design swarm behavior based on just a few key parameters. This involves looking at how cooperation, interference, and feedback mechanisms shape collective decisions. The applications are vast. In robotics, swarm robotics uses these principles to design teams of autonomous robots. Imagine tiny robots working together on search and rescue missions, monitoring our environment, or even building structures. These swarms are designed to be robust. They keep working even if some robots fail, and scalable, meaning you can easily add more robots to the team. Scientists are even exploring ideas like fractional calculus to make robot movements smoother and more coordinated within a swarm. Beyond robots, these mathematical insights are solving complex problems elsewhere. Optimization algorithms inspired by ant foraging or bird flocking are used in logistics, network routing, and machine learning. And get this, researchers are even studying human swarms, where networked groups of people, guided by these natural principles, can collectively answer questions and make predictions with startling accuracy. Recent breakthroughs are also looking at how individual agent smarts contribute to the group's overall capability. Frameworks like active inference formulation help model how individuals, by trying to make sense of their environment and each other, lead to this emergent collective intelligence. It's helping us understand how cognitive abilities, like understanding others' intentions, can boost group performance. Of course, it's not all smooth sailing. Accurately modeling the sheer complexity of real-world swarms, with all their randomness, is a huge challenge. But despite these hurdles, the mathematical journey into swarms continues to yield profound insights. It reveals a universe where simple rules create extraordinary complexity, and where collective action far outstrips individual capacity. As we continue to decode these mathematical blueprints, we're not just understanding ants and birds. We're unlocking powerful principles to design smarter artificial systems, better understand our own collective behaviors, and maybe even tackle some of the massive challenges facing our interconnected world. The calculus of swarms is a language for understanding the distributed, emergent intelligence that shapes so much around us, and it offers a path to engineering our collective future.